Okay, today we're going to start our second topic in AP Calculus, and that is integrals. So our first semester was derivatives, and now we're going to do integrals. We're not actually going to calculate an integral today, but one of the things we can do with an integral is find the exact area underneath a curve. So let's say we had this curve down here. It's just a function, and we're trying to find the area from x0 to x4. Well, we can use an integral to find the exact area underneath that curve. But since we're just starting off, we're just going to estimate the area underneath a curve, and we're just going to do it with rectangles. So basically, we're just finding areas of rectangles today, and that's it. Now, when you estimate the area underneath a curve with a bunch of rectangles, that's called a Riemann sum. And there's three ways that we're going to do that. We're going to do it with a left rectangular approximation, where the height of each rectangle touches at the left corner. We're also going to do it with the right rectangular approximation, where the height of each rectangle touches at the right corner. We're also going to do a midpoint rectangular approximation, where the height of each rectangle touches right at the middle of the rectangle. Now, you probably won't see these two on the AP test, but just in case you do, let's just see what they are. The upper rectangular approximation is where the rectangle touches at the highest point possible. That could be on the left side, it could be on the right side, or it could be anywhere in the middle. The lower rectangular approximation is where the height of each rectangle touches at the lowest point possible. Again, that could be on the left, it could be on the right, or it could be anywhere in the middle. You will most likely not see those two on the real AP test. Okay, the last one that we need to know how to do is called the trapezoid rule. Those are not rectangles, they're trapezoids. And because they're not rectangles, we're going to say that they are not Riemann sums. Now, the trapezoid approximation is something that we have to know how to do. All right, now let's go ahead and do some of these examples. Okay, for our first example, we're going to do a right rectangular approximation. And it says n equals 6. So what that means is we're going to use 6 rectangles. And we want to estimate the area under the curve from 0 to 6. So that's the shaded region. The first thing we want to do is we want to figure out what is the width going to be. So it's always going to be b minus a over n. The b is the endpoint, so that's 6. The a is the starting point, so that's 0. And the n is the number of rectangles we're going to use. So we're going to use 6 rectangles, so I'm going to divide by 6. Okay, for this example, I get 6 over 6, which is 1. So the width of each rectangle is going to be 1. So I'm going to do that in blue. Now the height of each rectangle is going to be the top right corner of the rectangle. So for example, for the first one, you have when x is 1, y is 6. So 6 is going to be the height of that rectangle. For the second one, when x is 2, that point is going to be at 9, so the height would be 9. When x is 3, the third rectangle has a height of 10, so we'll put a 10 for the height. The fourth rectangle has a height of 9, so we put a 9 for the height. The fifth rectangle has a height of 6, so we'll put 6 for the height. And the last rectangle has a height of 1, so we're going to put 1 for the height. If we add this all up, we get 41. Now on the AP test, there are 3 different ways that you could get this data. One way would be from the graph itself, another way would be from the equation, and a third way might be from a table of elements. Now we talked about the formula for the width. The width is going to equal b minus a over n, so that'll give you an equal width for each rectangle. If you want, you can use the formula. Whenever you have equal widths, there's a formula that you can use. Let's take a look at that. The formula would be the width times all the heights. So in this case, the first height was 6, the second height was 9, the third height was 10, the fourth height was 9, the fifth height was 6, and the last height was 1. The width of each rectangle was 1. So you see, if you add that all up, you get 41. Now there is another way of writing the heights for this example. Height 1 is actually f of 1, height 2 is f of 2, and so on. Now remember, you should only use this formula if the widths are equal. Sometimes they'll say uniform widths, which means they're all the same width. All right, now let's do this one with the graphing calculator just to see how it comes out. I'm going to start by typing my function in y1. Then I'm going to go to the home screen. I want to do the width, which was 1, times all the heights. My first height is going to be the right height, so that's when x is 1. So I'm going to do y1 of 1. My second height is when x is 2, so I'm going to do y1 of 2. My third height is when x is 3, so that's y1 of 3, and so on. all the way to y1 of 6. And we'll push enter, and you see we do get 41. Okay, let's go to the next example. Okay, for this example, we're going to use a left rectangular approximation with n equals 2, so that means just 2 rectangles, but each rectangle is going to touch at the top left corner. Let's try to use our formula to find the width. Remember, it's b minus a over n. The b is the endpoint, so that's 6. The a is the beginning, so that's 0. And we're dividing by 2 because we have 2 rectangles. This is going to give us a width of 3. For most of us, that's common sense. But if it was a more difficult example, this is the formula that you would use to figure out what the width is. So we know our width is going to be 3. And if we use the formula, we can do the width on the outside and then times the 2 heights. Our width is 3, and our first height is going to be f of 0. Our second height is going to be f of 3. F of 0 is 1, and f of 3 is 10. This estimate is going to give us 33, and that's it. Again, if you wanted to find f of 0, you could either just look at the graph if they give you the graph, or you plug a 0 into the equation if you have the equation, or from the table, you can see when x is 0, y is 1. You can see I've drawn my 2 rectangles underneath the table, and these are the 2 left endpoints. The first one happens when x is 0, and the second one happens when x is 3. Again, let's do that with a graphing calculator, see what we get. Again, you want to type your function in y1. It's the same function for us. Go to the home screen. You want the width on the outside, which was 3, and then times all the heights. The first height was when x is 0, so we're going to do y1 of 0. And the second height was when x is 3, so we're going to do y1 of 3. Then we just push enter, and you can see we get 33. Okay, we're still estimating the area underneath the curve from x equals 0 to x equals 6. So it's the blue shaded region. This time we're going to do a midpoint rectangular approximation. And here it says n equals 3, so it's going to be 3 rectangles. Okay, remember the formula for the width. It's going to be b minus a over n. B is the endpoint, a is the beginning, and n is the number of rectangles. So the width for each rectangle is going to be 2. So we can put a 2 for the width. Remember, to find the height for each of these rectangles, you got to choose the x value in the middle of each rectangle, and you're going to use the height at that corresponding x value. So for the first one, the height will be 6. For the second rectangle, we start from x equals 2 and we end at x equals 4, so the middle will be 3. So when x is 3, the height is 10, so we're going to use 10 for the height of the second one. For our third rectangle, it starts when x is 4 and ends when x is 6, so the middle would be when x is 5. So the height when x is 5 is 6, so that'll be our third height. We add this up, we get 44. So that's our midpoint rectangular approximation. Let's plug this in a calculator, see what we get. Remember, we want to type our function in y1. Then we go to the home screen. Our width is going to be 2. Then we're going to have 3 heights. First height is when x is 1. The second height is when x is 3. And our last height is when x is 5. And so you see we get 44 for our midpoint rectangular approximation. Okay, I wanted to point out that they're going to tell you that it's a midpoint rectangular approximation, and they're also going to tell you how many rectangles to use. So you're not going to choose that. Okay, now we're going to move on to the trapezoid approximation. Remember, these are not rectangles, these are trapezoids. So this is not a Riemann sum. This is a trapezoid approximation, and it even has different formula. Okay, first we're going to start off with the formula for just one trapezoid. The area of one trapezoid is going to be the width. So in our case, the width will be the bottom, and then times the average height. How do you get the average height? Well, you just add up the 2 heights and then divide by 2. So let's do an example over here. In this case, the width is 5, and then times the average height. So we got to add up the 2 heights, 6 plus 8, and then divide by 2. 6 plus 8 is 14. So if you divide by 2, you get 7. So the area of this trapezoid is 35. Now let's go to our trapezoid example. For this one, they want us to do n equals 3. So that means they want us to use 3 trapezoids. So our width is going to be the same thing as we had on the previous example. We already solved it. We got a width of 2. Now if we wanted to find the area of each trapezoid separately, it's going to be the width, which is 2, times the average height. So let's look at the average height. This height was 1. This height is 9. So I'm going to do 1 plus 9 and then divide by 2. So that's going to be 2 times 5, and so that's going to be 10. The area of the second one is going to be the width, which is 2 again, times the average height. So that'd be 9 plus 9 over 2, and that's going to give us 18 for our answer. For the middle one, you could also just do the area of a rectangle, and that would be 2 times 9, which is also 18. Okay, for the last one, the width is 2, and the average height would be 9 plus 1 over 2. You'll notice that's the same as the first one, so we're getting 10. So you don't actually have to use the formula, even though there is a formula for the trapezoid rule. You could just solve individually for each trapezoid and then add them all up, and you get 38 for your answer. Now, if you wanted to use the rule, let's have a look at what the rule is. The rule would be width over 2 times all 4 of these heights. So when I say all 4 of these heights, I mean when x is 0, when x is 2, when x is 4, and when x is 6. So we're going to multiply by all 4 of those heights. And then we have to double all the middle heights. So we're going to double this one and double this one. So we double all the middle heights. Now there is a second formula. You'll notice there's a 2 on the bottom here. So it's kind of like a 1/2. And if you distribute that on each piece, then you would get this formula. And a lot of people think this is easier to remember because it's just the width times all the heights, but you just multiply the first height and the last height by 1/2. Let's plug everything in. Our width was 2. The height when x is 0 is 1. The height when x is 2 is 9. The height when x is 4 is also 9. And the height when x is 6 is a 1. If you multiply all this out, you get 2 times 19, which is also 38. Now, if the formula is too confusing for you, then just calculate the area of each trapezoid individually. You'll get the same answer. Let's type this in our calculator and see what we get. Remember, you're supposed to type your function in y1. We have our function there, so then we go to the home screen. We're going to do our width times 1/2 times y1 of 0 plus y1 of 2 plus y1 of 4 plus 1/2 times y1 of 6. Then we push enter, and we get 38. And that's it.